selection a little shorter than usual because I have trying to create a day here. So that's creepy. All right, so let's get started. So a little bit of a recap. We've been talking about our solar system, and I gave an overview. We're going to go into more detail on each of the planets. With the overview. Inner terrestrial, the outer Jovian. Okay. There's the same number of them, but that's just a coincidence. Surfaces that you can stand on, and then these big Jovian gas giant planets that are much less dense, gaseous, large. And as we'll see today, that is not a coincidence. That there's a pattern of composition. There's asteroids, comets. Asteroids are made of terrestrial stuff. They're rocky. Whereas comets, as we'll see, are made of more Jovian planet stuff. And they are out with the Jovian planets. They are ice rich. So there's a pattern of composition. And there's also a pattern of motion. And I'm giving this overview because we're going to explain both of these today. The pattern of motion is that everything, with just a few exceptions, 3 exceptions, everything in the solar system is all orbiting in the same direction, counterclockwise when viewed from the North Pole down, rotating in the same direction. And all the moons are also orbiting in the same direction. So the sun rotates in the same direction, the Earth rotates in the same direction, its moon rotates in the same direction. The Earth orbits around the sun in the same direction, and the moon orbits around the Earth in the same direction. Okay? And this is not a coincidence, as we'll see. Okay, so this just expands out to the whole solar system. It's all the same, except remember there's just 3 exceptions. There's Neptune's moon Triton. There's Uranus that's on its side, so it's not really rotating in any direction with respect to from the North Pole down. And Venus. Venus is rotating in the wrong direction, although it's just very slow. So it's almost like it's not rotating at all. Okay, so as a reminder, right, there's this kind of composition. There's 2 major types of planets. There's these inner terrestrial rock and metal planets, and then outer gas giants, ice and gas, that we call Jovian planets. And then these swarms of smaller things never form planets. It's a rock, we call them asteroids, rocks and metal, and then ice-rich objects that we call comets. And the comets are out there further away, and the asteroids are closer in to the terrestrial planets, which makes sense. The same pattern of composition, okay? Pattern of motion. Everything is moving counterclockwise when viewed from the top down, meaning Polaris, the North Star, looking down on our solar system, with just those 3 exceptions: rotation of Venus and Uranus. Uranus because it's just on its side, and Venus because it's rotating very slowly in the opposite direction. And Neptune's moon orbits in retrograde, meaning the opposite of the normal way. Okay. And as we'll see, it's not surprising that there's a few exceptions. Okay. So the theory about all of it that explains all of this is called nebular theory. That is, our solar system began as a big cloud of gas and dust. This nebular theory, now the word nebula derives from cloud, because if you look up in the sky and you see these fuzzy things that look like clouds, and they get the name nebula for cloud. And this theory can be traced back to Kant and Laplace in the 18th century, that our solar system all just formed from a big cloud, right? They discovered gravity. So, right, all things gravitate. And so there's just this big cloud of gas and dust. And denser regions under gravity begin to contract, okay? And as we'll see, we now know this happened over 5 billion years ago, okay? And so the denser regions keep contracting more and more until you get to the center of the sun. And then as we'll see, little smaller planets, right, gravity coalesces material into those little objects too. And as we'll discuss, there's a process that happens that you would expect anytime you have a bunch of say gas and dust contracting under gravity. And that's heating, spinning, and flattening. All of these are consequences of some of the basic laws of physics we've talked about so far. So one is rotate, spinning. So just like a figure skater, you pull your arms in, you speed up. Okay, the same thing happens. It starts out rotating just in some random direction, a little bit, but as it contracts under gravity, it's like that ice skater pulling his or her arms in, and this is a consequence of conservation of angular momentum. Angular momentum is always the same, but angular momentum is, remember, distance from the center of rotation times velocity. I want to see one. So start out with
stop doing this. Water on the keyboard. That's bad. Give me a tissue.
It's a small distance from the axis of rotation.
No, Joe, that's so fun. Did you even do your paper plate?
Has to get pulled in. Okay, so now a spinning
I want
object. This
What's the paper plate? Did you do it?
As we'll see, this explains why everything's spinning in the same direction. Next thing is flattening. Okay, you have all of these random motion.
Did you do your paper plate?
This gas dust all orbiting in random directions, but they start to knock into each other, right? They knock into each other until they knock everything else out except for everything that's in each disk, all orbiting the same direction, with circular orbits. And we'll see some diagrams explaining why, but you can just think of this as, hey, if everything's orbiting randomly, not in circular orbits, they knock into each other, knock each other out of the way until if you're in nice concentric circular orbits, you no longer knock into them. Finally, the temperature increases, it gets hot. So as this cloud of gas and dust is contracting, spins up, it flattens, so it's forming a spinning disk. But you have all this, we talked about energy, you have this gravitational potential energy. It has to go somewhere. You're losing potential energy as things fall. And where does that energy go? It goes into heat. It heats up, okay? So this gas, in the center of this disk of gas and dust, things get really, really hot. Okay? And we call this a protoplanetary disk, okay? And for us, it happened over 5 billion years ago. And then it began to cool, okay? And as we'll see, as it cooled, stuff that was originally above its melting point began to condense, okay? Metals began to condense and freeze out into rock. Ice that was initially vaporized and then became liquid and then froze, right? Becomes balls of ice. And all this stuff begins to coagulate and accrete into what we call little planetesimals and then eventually the planets. So that's the overall nebular theory. So first is this formation of this protostar, which is in the center, and the planetary disk, we call it. This is the disk of gas and dust that will eventually become the planets. Okay? So it's initially this large cloud that starts to collapse. Remember, conservation of angular momentum tells us that the cloud will spin faster as it collapses. Due to conservation of energy, it's losing potential energy. Where does that energy go? It heats up. And then it flattens, okay? Because you have collisions between the particles. So eventually one direction of spinning wins out. Because if you imagine, suppose you had a disk spinning this way and a disk spinning this way, they're going to collide. So eventually they knock each other all out until one wins. The one that has the most angular momentum wins. And you end up with just a thin disk. And this explains, as we'll see, why all the planets orbit in the same ecliptic plane. So the disk flattens, heats up, spins. Okay. Here's an example of a nebula. This is a famous one. It's in Orion. So it's called the Orion Nebula. So if you look up at Orion, there's this beautiful nebula, okay, this glowing cloud of gas and dust. We'll talk more about these later, explain what the colors represent, as well as these darker clouds. These are star-forming regions. In fact, this is about a 2,000 solar mass star-forming region. It's destined to become a cluster of stars, okay, in about 100,000 years. This will be a big cluster of stars when all of this gas and dust turns into little solar systems. And if you look up at near Orion's belt, if you have a long exposure photograph, you can see.
What the heck?
Here's an artist's impression of what a protoplanetary disk would look like. So in this
Can
case,
you
you
stop?
have the flattening happen. It's heated up. You see in the center, you have a protostar, and it's spinning, and you're beginning to have accretion, which we're about to talk about. That is, you're beginning to form little clumps that are starting to carve out lanes, and maybe those clumps are just planets. And what's amazing is we now can see evidence of this process happening. We can look out with our telescopes, and we can see examples of protostars and protoplanetary disks where you have a nebula that's just entered this process of flattening, spinning, heating, and it's beginning to form protoplanets. So here's a famous example. Beta Pictoris is a star, and we're looking at this protoplanetary disk side on. So side on, there's this dust lane that's exactly what you'd expect, a flat disk of dust. The star is in the center, and the star is very bright. So what they've done in this photograph is they've zoomed in on the center, blocked out all the light from the star, as well as all that dust, and also rotated it, what was edge on, they've rotated it sideways so you can see kind of the forming solar system. And what we see is what we call—
Can you stop? Can you stop?
Being formed, and it's carving out little lanes that you can see in this protoplanetary disk. So we're actually seeing
What's wrong with you?
the formation of planets in this disk of debris.
Professor,
Yeah.
how long does this take place? Like, is this millions of years? What's the timeline here?
Yeah, it's millions of years, but that might sound long, but that's actually not very long in terms of the length, the 5 billion years length of the solar system. But yeah, it's on the order of millions. We'll talk about a little bit more about that as this lecture goes on. Here is a neat thing, because this Beta Pictoris b, this planet orbits its star every about 20 years or so. And so every year we can take a photograph of it. You can actually see a time lapse here. And again, if we blocked out the bright central star, because otherwise it would overwhelm the photograph. But this is this planet, this Beta Pictoris b. And as you watch, as the years go on, it starts to fall inward towards the star. And actually, in 2018, we saw it cross to the other side of the star. In fact, here, if I click on this, I should get kind of a video. Yes, please. Video. And so we're watching this, what we call an exoplanet, a planet around another star orbiting that star that is in its infancy, that is just formed. And this is still an area of astronomy that it's an exciting time, because we're still finding more examples like this. And there's several others. So here is another circumstellar disk. Again, these photographs look a little wonky because you have to block out the central star because it's so bright, because you're really just interested in that disk around the star. And it's also what you try to do.
You're gonna pass it. You're gonna pass. It's gonna pass.
Digital.
It's gonna pass.
You can see the side view. So here's the side view where we see these lanes being carved out by a photo. Here's another example. This is a really beautiful one. A protoplanetary disk, kind of exactly what you'd expect. Here's one where luckily we're not seeing an edge on, we're kind of seeing side view of or front view of a warm central region where the star is forming, and these protoplanets, we would call them, beginning to carve out little lanes in the ring of dust and gas. So those will form planets, and this central region will turn into a star. And so, yeah, the time scales are millions of years, but that's so that's too long for us to like wait and see suddenly the star turn on. And we'll talk about that process later. The nuclear fusion begins in the core of the star. But we can watch, like I showed you a few minutes ago, over decades, we can watch as these protoplanets begin to orbit around. Now, this is a reminder when we talked about gravitational orbits, right? We talked about how gravitational orbits are generally ellipses. And then there's also other trajectories that are part of this family of slices of a cone. And if you slice a cone sideways enough, you get unbound orbits, which correspond to hyperbolas. So they look like these purple trajectories here. Those are the sort of trajectories you would get if something came in from outside of our solar system and come near our sun and then slingshot out, go along on its way and never come back. But our planets have elliptical orbits. And this is true for any set of orbits. So in like this protoplanetary disk, forming your solar system, all those little gas and dust particles, they all have gravitational orbits. And initially, they all have kind of random directions. Some are very elliptical, some are circular. They're all in different directions. But one thing to understand is what's this initially a spherical cloud of gas and dust ends up being not only a thin disk, but you eventually have nice, close to circular orbits. Now, they're still slightly elliptical, but they're all, like in our solar system, most of the orbits, if you just draw them, they look close to circular. Okay? And that's why it took actually a very long time before people realized that the planets orbited on ellipses. It took until Kepler discovered that they were ellipses rather than perfect circles, as the Greeks believed. The process by which this happens can be understood by realizing that if you have circular orbits, the planets don't run into each other, right? You have a nice circle and then a circle outside of that circle, they never touch each other. But if you have elliptical orbits, they can intersect, okay? So early on when you're forming the solar system, those little bits of gas and dust, they're all constantly hitting each other and knocking each other away until you're left with just the orbits that are circular. Okay? That's why you end up with this nice sort of picture here of a disk. It looks kind of oval shaped because we're seeing it sort of side on, but these are all circular shaped orbits. Because if they're elliptical, they would intersect and knock each other out. So that's the process by gradually, over thousands and even millions of years, this protoplanetary disk has circular motion, okay? And it's all orbiting in the same direction. And as all of this gas and dust is kind of swirling in that same direction, the same process happens on smaller scales. So you have the sun in the center, the densest, hottest region of this protoplanetary disk. But you also have all that swirling stuff around it, and you have denser regions. The denser regions will become planets, and they themselves have material that's sort of swirling around them in that same direction. And as they begin to, you start out with a region that's just a little bit denser, so gravity pulls stuff in, then that process kind of runs away, right? You keep pulling stuff in because you get more and more gravity. And then you start carving away all of that material in your kind of path, in your orbit. Okay? You say that you start accreting material. Okay, so we'll talk a little bit about that in a second. But what material are you accreting? Well, what's the composition of the solar nebula? Okay, so most of everything in the universe, and including our solar system, is hydrogen and helium. 98% of the mass is hydrogen and helium. Why? Those are the simplest elements. That's what was formed after the Big Bang. Okay? All the other elements are formed in stars. So you have to have stars living and dying to produce all of these other elements. But hydrogen and helium, that's most of the universe. 98% of our solar system is hydrogen and helium. That ends up forming the sun. The sun is lots of hydrogen and helium, but also those gas giant planets. Okay? So 98%. Next, you have lots of hydrogen compounds. Okay, this is stuff like water. Water has hydrogen, H2O, ammonia, NH3, lots of hydrogen, methane, CH4, lots of hydrogen. And these, so I have a column here that says the condensation temperature, because this is relevant to this compositional pattern of our solar system. That is, hydrogen and helium are always gases. Okay, they can't form planets on their own. Okay, because they're too diffuse. They don't want to gravitationally condense into like a liquid or solid that can then bring other stuff into. Okay, it has to be kind of the other way around. You have to have something with gravity, and then you can get gas coming in around it. So the hydrogen compounds do, if they get cold enough, they can freeze, right? Like water, ammonia, methane. If they get cold enough, they freeze into ice, and that ice can form a planet around which things like gas can then be gravitated toward. Okay, that makes the next most amount of abundance in our solar system, 1.4%. That's because it's mostly hydrogen. Okay. Next, less common is rock, okay, and metals. And these, when they're hot enough, they're vaporized in liquid, but eventually it'll cool down and can form planets. Okay, and when it can form solid when it reaches between, around 1,000 degrees Kelvin, right? Is when rock becomes solid. Okay, and we'll see that's relevant to formation of the planets, the terrestrial planets, in a second. So they make up less, about 0.4% rock and about 0.2% metal. And any questions so far about composition? Okay, so here's a question we'll go through together. So which of the following lists the ingredients of the solar nebula from highest to lowest percentage, right? So this is just remembering what was on that previous slide. Okay? So there's the most light gases, hydrogen, helium, we call these really light gases. Next most are these hydrogen compounds that generate ice in the solar system mostly. Planet Earth is an exception. We have liquid water, but everywhere else it's too cold. It forms an ice. Rocks, and then metals. Metal, right? So on Earth, we're familiar. We think everything's made of rock and metal, but no. Terrestrial planets are just a small percentage of the solar system. Okay, so here's a question for, given what we just went over, for your participation. Ask. All right, what percentage of the solar nebula's mass consisted of hydrogen and helium gases? I'll give you 5 more minutes, 5 seconds.
How many?
Okay, everyone voted. And most people got the correct answer, right? As we just went over, most of the stuff in the whole universe is hydrogen and helium. Most of the stuff in our solar nebula is hydrogen and helium. What do I mean by most? 98%. Okay? And that ends up being what the sun is mostly made of, right? The sun makes up most of the mass in our solar system, right? And that's hydrogen and helium. And as we'll see, also the big gas giant planets are made of the same stuff, mostly hydrogen and helium. And how do we understand this? Why is it that we have these inner terrestrial planets that are made of rock and metals, which is the least amount of stuff in the solar system, and then these big outer Jovian planets that are made of gases and ice, and they're big. There's a lot of that hydrogen out there, right? Which makes sense because that's what the solar system is mostly made out of. So a way to understand this is that solar nebula, remember we talked about it heats up, right? It's hot initially. So the center of the solar nebula is the hottest. And as you go outward and as things are cooling off, it's hottest near the center and it gets cooler and cooler the further you get from the center. And there's going to be what we call a frost line. Early on in the solar system's formation, there's an area closer to the sun. It's hotter, okay, where you couldn't form ice, okay? It was too hot for ice. But it did cool down enough for rocks and metals to go from liquid to solid, right? So you have solid balls of rock and metal close to the sun that could start accreting and forming planets. Those become the terrestrial planets. And that's everything within the frost line. That is anything hotter than about 150 degrees Kelvin. Okay, and that frost line is between Mars and Jupiter. Okay? Everything past the frost line, so that's where all those big gas giant planets are. Sure, you can have rocks and metals, but crucially, it's cold enough for those hydrogen ices that form the most stuff in the solar nebula besides hydrogen and helium. There's much more of it, the terrestrial material. That stuff can condense and form ice. So you get big balls of ice that can form planets up. And those big balls of ice are much larger than the terrestrial planets. So they can form a lot of gravity and pull in hydrogen and helium, right? That is forms the majority of matter in the solar system. So that's why they're so big. So this understanding explains why there's this pattern of composition, why the inner terrestrial planets are made of rock and metal, and why the outer Jovian planets are made of ice and gas, and why they're much larger. Okay, so this is a page kind of recapitulating what I just said. That is terrestrial planets. Okay, small particles of rock and metal were present inside this frost line, and they could condense out. Right, it cooled off enough that you get little clumps. Okay, and these build up, they collide, and they accrete into, and then gravity pulls them together, and they accrete to form planet testicles. Okay, that can form these terrestrial planets. Past the frost line, ice is part of it. I mean, you still have rock and metal, but there's a lot more ice that could form. So you get really big planet testicles. We call it like dirty ice because there's still some rock and dust and metals, but mixed with lots of ice that formed the cores of what became these large gas giants. Because they have enough gravity that can pull in all that hydrogen and helium that otherwise wants to escape. On Earth, if you pop a helium balloon, that helium actually just floats out into space. We don't have enough gravity for the helium to stay onto the surface of the Earth. That's actually why we have like a helium shortage, if you've ever heard of that. Okay, so this is a process called accretion. So you have the sun in the center, right? And you start off with just all these little bits of inside the frost line, these little bits of terrestrial material, little rock, grains of rock and metal. Gravity pulls them in. They begin to form a ball under gravity, and then that stuff accretes. Things collide, smash together, and then you can carve out your lane. And then gravity gets stronger, and you pull in more stuff, and you accrete to form your planet. Okay? The same process happens past the frost line, but you have mostly, in addition to little bits of metal and rock, you have a lot of ice crystals that are forming big snowballs that then collide and accrete to form planet. Now, you can imagine in this period, okay, during the beginning of the solar system, it's gonna be because this process of accretion means that you're constantly bombarding. The planets are constantly being hit by meteors. And as we'll see, when you look at something like the moon and you see all these craters, these meteor craters, those are not recent. They're almost all 4 to 5 billion years old, because this is when it was all happening. This is when the solar system had so much stuff smashing into each other. And one of those things is particularly relevant to the Earth, which was that we think that the moon is actually a captured, well, basically a collision between the Earth and a pretty large planetesimal, okay? So basically a Mars-sized planet called Theia and something that you might call pre-Earth, I think collided.
Oh my God.
This is actually what formed the moon. So our understanding is that the cores of these two planets merged and the mantle of the Earth was ejected and later formed the moon. And remember, we learned because of the tidal force, the day on Earth keeps getting longer. So this, extrapolating backward, the Earth and moon were moving very quickly. In fact, the Earth a day long was only 5 hours. Okay? And actually, this theory is borne out by the data. So we're going to talk about things like radioactive dating from isotopes. One use of looking at different types of what we call nuclides or isotopes is you can look at moon rocks. Luckily, we brought
Oh my God. Did you wet your bed?
and you see that they have the same
You
isotope.
sure?
In other words, it looks like they came from the same stuff. Okay, the density of Earth is much higher than that. The moon, actually, the density of it is about the same as the Earth's mantle. So that makes sense. And then also, the moon couldn't have formed around the Earth naturally. It has too much angular momentum. It's too large relative to the Earth. It's moving too quickly. So it actually, so it wouldn't have formed naturally. It actually had to have been an impact like this to have formed. So this is called the giant impact hypothesis. During this period, when the solar system was a very chaotic place, you even have things like these big planets smashing together. And that's actually the origin, we think, of those 3 exceptions we talked about in the solar system. Right? For example, Neptune's moon, Triton, right? It's moving in the wrong direction. Well, it's probably just a captured asteroid. Similarly, like, Venus, like Venus maybe orbiting slightly in the wrong direction is probably a big collision.
What the heck they doing up there? They're running? Huh?
Here's an illustration of this, the relative sizes of the pre-Earth and Theia colliding. Would eject this mantle material, forming a ring around the Earth. That ring would slowly coalesce and eventually accrete to form the moon. Now, a little bit after that, there's evidence that there was a specific time after things had started to settle down where things got really chaotic. This was where all the surfaces of the planets, like the moon's surface, were totally cratered by what we call the late heavy bombardment. Late because it was a little bit later than when things were initially really chaotic in the early solar system during all this accretion. And we learned this because of the moon rocks we brought back from those Apollo missions that show that the surface of the moon was formed about 4 billion years ago, whereas we know that the moon itself was formed about 4.5 billion years ago. So something happened about 4 billion years ago that resurfaced the moon. And basically, there's a whole lot of meteors around 4 billion years ago that called the late heavy bombardment. Okay? This would have impacted all the terrestrial planets. So there's one tells you couldn't have much life on planets about 4 billion years ago. There's huge numbers of meteor impacts. One hypothesis is that simulations of how solar systems
Bring bad babies on your
gas
home.
giant planets often migrate. And when they do that, they bring with them a whole bunch of debris. So we think that probably early on in the solar system's history, the gas giants moved in their orbits a little bit, slingshotting material towards the inner planets. All right, so we've talked about a number of things. Okay, we've talked about orbital characteristics. We've talked about compositional differences. We've talked about asteroids, comets. We've talked about just now the craters on the moon and stuff, all being part of this explanation of all of this coming from nebular theory, the theory that initially the solar system was just a big cloud of gas and dust that began to contract and spin and heat up. So here's a question for your participation. And which of these does that nebular theory not predict? It predicts everything on this list except for one.
Nó hầm vào lên.
5 more seconds.
Didn't say nothing about the moon.
Okay. And so this is correct. So majority of people said
Oh.
that it didn't predict the equal number of terrestrial planets. That's correct. As I said, that's just a coincidence, right? That equal number. It could have been any number of terrestrial versus Jovian planets. But what it does predict, planets orbit the sun in circular orbits in a flattened disk, meaning all roughly in the same orbital plane. It explains the compositional differences. The inner planets are rocky and metallic. The outer planets are large, ice-rich, lots of hydrogen, helium. It explains the presence of asteroids and comets. Why? Well, asteroids are just rocky debris that never accreted to form a planet. Comets are just icy debris that never accreted to form a planet. And it explains the craters on the moon, which are
Oh my God!
due
I'm in
to
class, y'all.
all this chaos. 4 to 5 billion years ago, there was all this debris around that hadn't yet been accreted. Any questions so far about nebular theory? Right, the overall idea: cloud of gas and dust, spinning, flattening, heating. Okay, inside the frost line you get terrestrial material. Outside the frost line you get ice. They begin to form protoplanets and accrete, form larger and larger bodies until you clear all the paths out during these periods of bombardment, leaving behind a little bit of debris, asteroids, in the inner regions, comets, in the outer region, and then the inner terrestrial planets, in the outer region. Okay, so as a summary, okay, you have rocks, metals, ices, it's outside the frost line, but only rocks and metals inside the frost line. That's the difference between the inner terrestrial planets and the outer Jovian planets. Yes, start out with just small particles, and they collected. The planetesimals then accreted into planets. Planets inside the frost line made of rock and metals, but additionally, outside the frost line, you have lots of ice, much more ice, that could form these giant planet testicles that are ice rich, that can pull in all the hydrogen to get them really large. And then finally, the solar wind, which was actually much stronger early on in the solar system, blew away any extra gas, leaving behind kind of this vacuum of space, more or less. Not much going on between the planets anymore, except for asteroids and comets. And then the gas has been kind of gobbled up by those gas giant planets or blown away. That's because of the solar wind, that the sun has a solar wind, which we'll talk about when we talk about the sun specifically, that kind of, the sun is constantly ejecting what we call the political wind of particles zooming away from the sun. And when we look at young stars, which we can do with telescopes, we see that young stars send out the strongest solar wind, which kind of tends to blow away on that extra gas out of the solar system.
Go back in, man.
Okay, great. So we talked that there are these few exceptions to the general pattern of the
Why are
Venus
you out here? Go back in.
Uranus is tilted on its side. Neptune's moved right from its but all of this makes sense.
Now don't get it.
In nebular theory, because you expect there to be some collisions. Right?
No!
You expect,
No! No! I'm
Hey!
gonna cut you. Don't do
Just
that.
like Earth collided with
If you get it by the wrong, okay?
Theia.
Keep on blowing it. You stop it.
Collided with Uranus, sign of Sol. Now, how do we understand the influence? Like, this is kind of a big
You go back in the room.
to learn, right? Has been here just a few thousand years, or a million, or a trillion years, right? Well, we've been able to.
But there's no food for you. Not now. Come again.
First of all, we can't wait.
Well, I'm done fast enough for you. How
So
go?
we use computer models to get a rough sense for how long this whole
Really
period of planetary
There's no
formation.
spaghetti.
It's less than 50 million years. So
There's
it
no
goes
soup.
50 million years.
What soup you making?
Totally getting into
There's no soup.
our current solar.
Why you out here?
And that's much less, it's a much smaller number, 50 million years, and 5
Why are you out here?
1%.
You're falling 5 years.
Basically, that's a flip.
What the heck? You put water in there?
I don't know how it is.
You stay there.
Explain how this works. But when we bring rocks to Earth from the moon,
After this time, you're gonna turn on my cam. You want to be on the cam? Get the heck out there.
Right, so if we could get their age when they first crystallized out of
You,
that
you,
hot,
look, you're gonna be on the cam, boy. Get the heck out. Wait until 2:10.
that's 4.5 billion years old.
Yes.
Okay, when we look at Earth,
Go in the room, yes. Go in the room.
are about 4.4 billion years old. So all of this points, all the evidence points to the solar system, meaning when everything cooled off enough to just first form these rocks. Being about 4.5 billion years. And that's about a third of this age of the universe. So how do we understand this? So one way is through meteorites. Have been relatively
After this, we go on the cam. You know, I don't want you.
formed, and then just
Get the heck out.
like,
Go in the room.
leaves the Earth. There's all this stuff going on, right? There's volcanic eruptions. There's the Earth
Go, man. Go, man. Yeah. Go, man.
actually it gets resurfaced every 100 million years.
Go in the room.
Tectonics, volcanism. But
Go in the room.
fossilized
No eating in the room.
But we can here's some examples of meteorites. So there's what we call kind of rock meteorites that have these kind of minerals that when they first form, they have like crystallized minerals, maybe various, like carbon compounds and things. You also have iron meteorites, like just chunks of iron from the early solar system. the general idea for how we learn how old something is through radioactive decay. Now, there's these types of atoms, types of elements on Earth that are decaying. They break apart through what's called radioactive decay, and they decay into other elements. So, for example, potassium-40. This is a type of potassium that has a half-life, we say, of 1.25 billion years. That means every 1.25 billion years, if you have like a cup of it, half of it will have decayed into either calcium or argon. Okay. So that means in twice that time, in 2.5 billion years, you're only gonna have you start out with a cup of it, you're gonna have half a cup after 1.25 billion years, you're gonna have a quarter of a cup after 2.5 billion years, and so on. And so as the amount of potassium goes down by half every 1.25 billion years, and the amount of calcium and argon goes up corresponding. So if you can know how much of potassium you started out with, how much calcium and argon you started out with, and your weight, and see how much potassium
Nó trống
goes
thôi.
up,
Nó hai bài à.
you know how old something is. So here's a walking through that with you. So like suppose you have a rock originally made of potassium-40, and half of it's going to decay every 1.25 billion years. Okay, and then you break open the rock and you find that there's 15 atoms of what it could have decayed into, calcium or argon, for every 1 atom of potassium-40. Okay, and from that, let's figure out how long ago did that rock form. Okay, you started out with 16, say, atoms of potassium, and you're left with just 1 atom. So what does that mean? So after 1.25 billion years, you're down to 8, because that's the half-life. After twice that, 2.5 billion years, you're down to 4 atoms of potassium. Now 3 times that, 3.75 billion years, you're down to 2 atoms. And finally, after 5 billion years, you're down to 1 atom of potassium. Okay. And so that's what we see, right? If you start out with 16 atoms of potassium, after about 5 billion years, you're left with only 1.
Go in the rock. No eating in the rock.
1 for every 15 of calcium and argon that are left behind. That's the basic idea, right? So if we see that, we know that that rock is 5 billion years old, and that's the basic idea behind radioactive dating. Now, in practice, the way we do this is, for example, called zircon dating, because this gives us a way to know how much of something started out in a mineral. Because zircon, this is a common mineral on Earth.
Don't think that.
Here, zirconium silicate.
Yeah, you shut up.
These minerals will allow, when it first cools off and forms a crystal, it will happily include uranium in its crystal lattice, but it won't include lead. So you will never see lead starting out in one of these crystals. And what that means is, luckily, the uranium that is in there decays radioactively. Uranium-238 decays after 4.5 billion years to half of its amount. And uranium-235 takes 700 million years to decay to half its previous amount. So what you can do, and what does it decay into? It decays into lead, which wasn't initially in the crystal. So by looking at how much lead is in the crystal compared to how much uranium is in the crystal, you know exactly how old that mineral is, because that lead could only have caught there by the radioactive decay that's accumulating by a certain amount every 4.5 billion years for lead-206 that you find from uranium-238. Every 700 million years from lead-207.
No.
Okay.
No potatoes.
Famously in 1956, dated the Canyon Diablo meteorite. Now, this is a famous meteor crater called Meteor Crater in Canyon Diablo in Arizona. This giant meteor crater, some tens of thousands of years old on Earth. It's one of the biggest classic looking meteor craters that's on Earth. Now on Earth, you don't see many meteor craters because, unlike the moon, the Earth is geologically active. So every 100 million years or so, the Earth's surface gets repaved. So you don't see very many, but here's one from a few tens of thousands of years ago. But the actual meteorite we found in the center of that crater, and here's a piece of it, it's an iron meteorite. Okay. And he used this technique to date that meteorite to 4.5 billion years old. What that tells us is that that meteorite that came from outer space, it was just floating around the solar system from when it first formed. So if we can know how old it is, we know how old the solar system is.
You bad.
We crafted the Earth so we can
You're not bad.
pick it up.
But it's black as old places.
4.5 billion years old. Okay. Yeah, he also used a more sophisticated analysis that I've shown here. That's kind of neat because there's a whole story about Claire Patterson that's really interesting because when he was working on these results, he found because he was trying to measure how much lead was in this stuff, but he kept getting contamination. He kept finding more lead than there should have been, and he realized that there's lead contamination everywhere from gasoline. Gasoline used to be leaded. So he actually invented one of the first clean rooms to try to deal with this. And he also helped clarify for everyone the amount of problems that were occurring through things like lead and gasoline. And helped pave the way for us to eliminate that, luckily, because that was, lead is a problem. And, when children are growing up, it affects their brains, right? So, in any case, so he developed a more sophisticated analysis that actually didn't even require knowing how much lead was initially in
What the heck?
by looking at the ratios of these two, because this stuff tends to imagine the stuff in this early solar system all had the same proportion of stuff initially. So had the same amount of uranium-238 as uranium-235. So what that allows you to do is use the ratio of the lead that came from the uranium decay to the ordinary lead contamination. And because these two have different half-lives, if you plot these two ratios on a graph, or different things like iron meteorites that don't have much, that are mostly just regular lead, compared to, say, stony meteorites that were mostly lead from uranium, because remember, those have these minerals that don't like to lead initially. If you look at the slope of these lines, using this method, the slope gives you the age of all of the stuff that formed the initial solar system. Okay? So this is the more sophisticated method that over and over again keep looking at not only meteorites, but also the stuff that the Earth is made out of, and see that the oldest stuff the Earth is made out of also forms data points that all lie along this line that correspond to the Earth, meteorites, moon rocks, all being between about 4.5 and 4.6 billion years old. Okay. So that's the current consensus about the age of the Earth. Before Claire Patterson, people thought it was about 3 billion years old. So we still had the right idea. But this was the first very precision measurement. We now know it's about 1%. All right, if not, like I said, I think I'm gonna end it a little early today. It's snowing pretty good out there. Make sure that it's ready for another snowstorm. All right, I'll see you once.
This early? Okay. You go sing a song, huh? This little thing says no, so no. Give it back. And okay, I'll put it. And I'll put the old up. No, I didn't. I got food. And, oh, I didn't.